today with a video because I will not be able to meet this Friday on Teams. So I'm creating a video for the next section in our Module 2, the first section in Module 2. You should be wrapping up Module 1, taking that exam, and ready to dive into Module 2. So I am coming to you with a video to go over 2.1. So I'll go back and forth between the problems and the lecture notes as I need to. So let's begin here with the notes. Let's just kind of introduce a little bit, talk about it a little bit. Excuse me. So, and this should say Module 2, my apologies. It says it down here. Module 2, Section 1 deals with polynomial functions and their graphs. So in this section, we'll be looking at some polynomial functions, identifying whether or not we have polynomial functions, recognizing some characteristics, determining end behavior, using factoring to find zeros of polynomial functions, identifying zeros and their multiplicities, several different things here, looking at the relationship between the degree of a polynomial and its turning points, and then graphing some polynomials. So first off, a polynomial is it has non-negative integers. Okay, so as far as the I guess I need to say, as far as the exponent, n is a non-negative exponent, I need to say, because your coefficients can be positive or negative. Okay, the coefficient is the number in front of the variable. But you'll easily be able to identify a polynomial because, first off, its exponents will be positive, and then also the variable exponent will have whole numbers. It won't be a rational exponent and it won't be negative. The polynomial function it'll be stated that it has degree n being the highest exponent, and the leading coefficient is the coefficient of that highest term. And usually we put it in descending order. Polynomial function of degree 2 or higher has graphs that are smooth and continuous. By smooth, we mean that the graph contains only rounded curves with no sharp corners. By continuous, we mean that it has no breaks. You don't have to lift your pencil to draw it. The end behavior. So that's one of the first things I think that we'll look at as far as the problems. One of the first couple. The end behavior, what the graph of the function is doing as we look at it from the left and from the right, far left and far right. Although the graph of a polynomial function may have intervals where it increases or decreasing, the graph will eventually either rise or fall without bound as we move far to the left or far to the right. The sign of the leading coefficient and the degree of the polynomial function will reveal its end behavior. So we call this the leading coefficient test. Some texts call it end behavior test, but for the most part, it is the leading coefficient test. So if you have a polynomial, as x increases or decreases without bound, the graph of a polynomial function will eventually rise or fall. In particular, the sign of the leading coefficient, a, and the degree n of the polynomial function will reveal its end behavior. So here is the leading coefficient test. So notice that when it is odd, the ends are in the opposite direction. When n is odd, which is the degree, okay, then the end behavior, the polynomial, is in opposite direction. If the degree is odd and the leading coefficient is positive, then the function overall will rise from left to right, where it falls on the left, and gets higher or rises to the right. So if you were to kind of pretend like this was just a straight line, it would be positive in that direction, heading upwards from left to right. So the left falls to the left, rises to the right. When the degree is odd still, but the leading coefficient is negative, it does the reverse of that. It will rise on the left and fall to the right. So it's as if you were kind of to ignore this middle part, what's happening here, and just kind of look at it from left to right, it would be decreasing. Rise high on the left, falling to the right. Now, for even functions, the end behaviors are in the same direction. If the degree is even and the leading coefficient is positive, then it will be up at both ends, rises on the left and rises on the right. If it's even and the degree is negative, then they will both fall to the left and fall to the right. So we're going to look at a couple of examples. Let's take a look at some problems here. So we've got one of the first ones. It's asking us to determine whether the function is an actual polynomial function. And we can safely say that yes, this is a polynomial function because the exponents are all positive integers, and integers being whole numbers. And again, they're positive. So they're not fractions and they're not negative. So number one, we would say that is a polynomial. And the degree, in this case being the highest exponent, is 5. Okay? Number two is asking us, is the displayed graph the graph of a polynomial function? Yes, it is. There are no breaks in the graph. If you were to take your pen or pencil, you could trace along this graph the entire time and not have to lift your pen. So yes, this is a polynomial function. Okay. Excuse me. Let's look at number 3. Use the leading coefficient test to determine the end behavior of the graph. So looking at this, it says, or the function is 5x to the 7th minus 2x to the 6th plus 2x to the 4th plus 7. So our degree here, the highest exponent, is 7, which is odd. Okay. And the leading coefficient here is a positive number. Remember, the leading coefficient will be the coefficient of the term with the highest exponent. Leading coefficient is positive. So this particular function, if we were to look at its graph, and you could actually on your calculator, if we were to actually examine its graph, we would anticipate that it would fall towards the left and rise on the right. I'm going to look at it here. So we've got 5x to the 7th minus 2x to the 6th. Coming down at the exponent, I press that arrow over key, plus 2x to the 4th. And remember, I'm using this key for my x. I'm using this key for my variable x. And I'm using this to move or place a number in the exponent, the little housetop or rooftop. All right, and then I use my arrow down or left, or right arrow rather, to come down at the exponent, then plus 7. So I'm going to look at the graph. Let's hit graph. And this is a standard 10 by 10 window. Hopefully we can see it, but we may have to zoom out to see a better picture. This is not terrible, but if you want to see more of it, you might want to adjust your window. The X looks like it's fine, but it looks like our Y, we actually may want to go from negative 20 to maybe 20 to see more of it. So I just adjusted the window. Yeah, and I can see a bit more of the graph. So you can see that it falls to the left and rises to the right. That would be A. Okay. Know if there's more than that on there as far as that. Yeah, it looks like that's the only problem related to leading coefficient tests. Let's go back to the notes here and see what's next. Okay, that was an example. All right, let's talk about zeros of polynomial functions. So when you take a function and you place it equal to zero, you're creating an equation. Normally, when we are dealing with equations, we want to solve them. So one word or one name used for a solution of an equation is called a zero. Okay, so if f is a polynomial function, then the values of x for which f of x is equal to zero. So basically, when you create an equation, you take the function and place it equal to zero, you create an equation. When you solve for those values of x that make that equation true, that make the equation when you place it equal to zero true, then those solutions, those values of x are called zeros. So zero is another name for a solution, okay? For a solution of the equation. So these values of x are called the roots or solutions of the polynomial equation. So roots is another name. Each real root of the polynomial equation appears as an x-intercept of the graph of the polynomial function. So in other words, if you were to take this function and you graphed it, your solutions or your zeros are actually where it crosses the x-axis, okay? And of course, we have an example. We'll take a look at this. It says find all zeros of f of x equals x cubed plus 2x to the second minus 4x minus 8. We find the zeros of f by setting f of x equal to 0 and solving the resulting equation. So we take that function and we place it equal to 0. Okay, whether you place the 0 on the left side here or the right, I usually put equal 0 here on the right. Okay. And then we are going to have to figure out what techniques we would need to apply that would allow us to solve for x. So one of the first things that I need you to think about here is that you've got four terms. When you have four terms, well, first off, when you're looking at a polynomial function, the very first step is to see if you have any GCF, any greatest common factor that you could possibly pull out of all the terms. Okay, whether you have two terms, three terms, or four terms, you always look for a GCF. There is no GCF here. Okay, there is no term that can come out of all four at once. So what we do then is we notice that we have four terms, and maybe perhaps we should approach this with factoring by grouping. And that's what's happening here. So what we do is we take the first two terms, and I'm going to work one. There should be one similar to this in the homework that we'll look at. It may or may not be exactly like this. But we're going to take the first two terms and we group them, and then we group the last two. And so ideally, we try to factor the first two terms, pulling out what's common to both of them. And that would be x cubed plus 2x squared. That would be an x squared that could come out of those two terms. And what that would do is leave us inside here a binomial that's formed by what's left. When you factor out x squared from x cubed, you have x. When you factor out x squared from 2x squared, you have 2. Okay? So then we go to these two terms. Well, notice that this binomial that was left here in the parentheses was just a positive x plus 2. So when you look for the GCF or the factor that's common to both of these terms, you want to not only pull out the 4, but pull out that negative 2, the negative 4 as well. So you're pulling out the negative in front of the 4 or with the 4 because you want this to then leave you with a binomial that's matching, okay? You want to be left within the parentheses with a binomial where they match up. They have a common binomial. So we factored out negative 4 that left us with x. We factored out negative 4 from negative 8 that left us with plus 2. So then we have x squared minus 4 and x plus 2 that we then place here as a product. So we form a binomial using the factors that we pulled out, and then times the binomial that they shared, that they had in common. And so we now have x plus 2 times x squared minus 4. And then we're able to solve these by placing each of these two factors, these binomial factors, setting them equal to 0 individually, and then solving. So x plus 2 equals 0 becomes x equals negative 2. And then x squared minus 4, we would take the 4 to the other side. That would leave us with x squared equals 4. And then we take the square root. So that would leave us with a plus or minus 2. So our solutions for this polynomial function would be -2 and +2, technically, because this is a plus or minus 2 over here. So your zeros are -2 and 2, but recall that the -2 actually was listed twice. So it had a multiplicity of 2. It was repeated. Let me go back here. It was repeated because it was here, and then it was also here. So you have two zeros, -2 and 2. The graph of this function would show that each of the zeros are an x-intercept. So you have the point, the graph passes through the point -2, 0, and at +2, 0. But notice how it looks different at each of these, okay? So at -2, we have it touching and turning, whereas at +2, it crosses. That is where we get into multiplicity. So if you have a solution, if you have a 0 with an even multiplicity, then the graph is going to touch at that point, touch the x-axis at that point, and turn around. If you have a 0 that is odd, that has an odd multiplicity, perhaps it's just, again, just one time listed as a 0, then it will cross the x-axis at that value. Regardless of whether the multiplicity of a 0 is even or odd, the graph tends to flatten out near zeros with multiplicities greater than 1. So here's an example. Notice that it's already in its factored state. So really what we need to do is just take each factor and set it equal to 0. So we have x plus 1/2 squared. We're going to place that equal to 0. And we have x minus 5 cubed, and we're setting that equal to 0. This -4 factor, if you were to place that equal to 0, it would not be true, so we just toss that out. Each factor is placed equal to 0 individually, except for the ones that are not true. -4 is not equal to 0, so we toss that. There's no variable, in other words, for it to solve. So the -1/2 has a 0 multiplicity of 2. Why? Because it has an exponent here. So you would technically break it apart and show this twice. X plus 1/2 equal to 0, x plus 1/2 equal to 0. So you would solve it twice technically, which means you'd have the -1/2 as a solution, as a 0 twice. So a multiplicity of 2. Here, notice that you have a cube exponent, which means you technically would have x minus 5, a factor of x minus 5, 3 times. So x minus 5 equals 0, x minus 5 equals 0, x minus 5 equals 0, so 3 times. Or in other words, solve it once and just say it has a multiplicity of 3, which is an odd multiplicity. So for this particular function, if we were to look at the graph of it, you would notice that it touches and turns at the 1/2 because it has an even multiplicity, whereas it crosses at 5. It does flatten out a bit because it has a higher multiplicity than 1, it's greater than 1, but it still crosses through. Okay? So at -1/2, it touches and turns, even multiplicity. And at 5, it crosses. Flattens out a bit, but it does cross. Okay, let's look at an example. Let's take a look at that. All right, how about number 5? Last problem we did was 4. Let's look at number 5. So with this problem, it says find the zeros of the polynomial function and give the multiplicity for each 0. Okay. It says state whether the graph crosses the x-axis, and it got cut off a little bit, or touches and turns at the x-axis. I'm sorry, crosses the x-axis or touches the x-axis and turns around. So it got cut off a bit, but we know what it's talking about here. Sorry about that. All right, so first off, it's already factored for us, which is beautiful, but I am going to take the function and place it equal to 0, 7, and I've got x minus 9, and then here I've got x plus 4 cubed. So I placed that equal to 0 to create the equation. Because remember, your goal is to solve the equation. You're looking for the solutions of the equation, okay? All right, so the first thing we do is we notice that 7 is a constant factor, but when you place it equal to 0, it's not true. So we toss that one. Then we have x minus 9 equal to 0, and then we have x plus 4 cubed equal to 0, okay? So x minus 9, there's just one of those. So let's just drop that, parentheses, and just solve. X minus 9 equals 0, which means x equals 9. So this has a multiplicity of 1. Okay, there was just one factor. Here, keep in mind the cube means 3 factors of that binomial. So it would technically be like x plus 4, x plus 4, x plus 4. And then you could break each one of those apart and place them equal to 0 individually. But they're the same factor, so they would have the same solution. So all we'll do is we'll just simply drop the cube and just solve that. X equals a negative 4, but we'll make sure that we state that it has a multiplicity of 3. Okay? So the zeros are negative 4 and 9. Okay? Negative 4 and 9. And I don't think the order matters, but I wrote the smaller one first. All right, then it says determine the multiplicity. Well, we already kind of did state that. So one of the zeros, there are 2 zeros. So we'll select C here. There are 2 zeros. Okay, there are 2. The multiplicity of the largest zero is 1. The largest zero is 9. It has a multiplicity of 1. And the multiplicity of the smallest zero is 3. The smallest zero is negative 4, and it has a multiplicity of 3. Okay? Then it says determine the behavior of the function at each zero. Well, they both have odd multiplicity, so they're both going to cross. They're both going to cross the x-axis. So we would say, or the graph would cross the x-axis at all the zeros. So we would say, or we would select C. And then, of course, you can always examine the graph if you like to verify it. So I'm going to type it in exactly how I see it, 7 parentheses, x minus 9, and then parentheses, x plus 4 raised to the third power. And I'll hit graph. And I did change my window before, so if we needed to change it back, we could, but it wouldn't even hurt to make it even, bigger as far as maybe both of them, maybe adjust them both. Let's make X go from negative 20 to positive 20. And let's let the Y maybe go from, let's zoom out a bit, negative 40 to positive 40, so that we can kind of, let me go back here. Apparently, I got my window, something wrong. Oh, I didn't put the negative in front of the Y. Negative 40 to positive 40. There we go. And we'll just get an even better picture a little bit. Okay. That's in behavior. I'm sorry. That is finding zeros and multiplicity there. Okay. Let's look at number 6. Let's look at one where we may have to actually factor. It says find the zeros for the given polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis, touches and turns around at each zero. So looking at this particular function, I noticed that right away, I should be able to factor out a GCF because I want to solve for the zeros. So anytime you're dealing with a polynomial function, sorry, anytime you're dealing with a polynomial function, you're attempting to solve it, of course, by factoring. And when factoring, you always look for a GCF first. So my GCF here would just be an x I'm going to pull out. And that leaves me with x squared. This is minus 36x. And then this is plus 324, which is a huge, huge, huge number. But that's okay. So what we're going to do now is try to, I'm going to go ahead and place this equal to 0. So what we're going to do now is try to factor this trinomial. We already have the factor x equals 0. So x equals 0 is definitely a solution. And then we need to get the others from what's remaining here. Okay, so this is what we have right now. So what I'm going to do is try to see what numbers I can use to factor 324 so that they'll add up to give me 36. Because according to the signs, my constant term is positive, which means I have like signs, and my middle term here, my b term, is minus, which means they're both going to be negative. So I'm going to go ahead and factor x squared as x times x, and I'm going to go ahead and put my signs in. So I'm looking for the factors of 324 that will add to give me a negative 36. So it's going to be a negative and a negative added up to give me 36. So let's just try some numbers here. Since it's 36, maybe let's see, is it divisible by 9? Okay, that won't work though. Let's do something bigger. Let's do 324. Let's try 18. 18 and 18, there it is. 18 plus 18 is 36. So x minus 18, x minus 18, okay? And then of course I already have that one. So two factors of x minus 18, you can break them apart. So x equals 18 with a multiplicity of 2. So your zeros are 0 and 18. So multiplicity of 2 here, whereas this one has just a multiplicity of 1. Okay? All right, so there are two zeros. Let's see, we're going to select B. There are two zeros. We're going to select B. There are two zeros. The smallest zero, which is 0, the smallest zero is 0. It has a multiplicity of 1. The multiplicity of the largest zero is 2. And then looking at the behavior at each, well, the graph will cross the x-axis at 0, and it will touch and turn at 18. So we're going to select A here because they have different multiplicities. They have one is even, one is an odd multiplicity. So when you have an odd multiplicity at that 0, it's going to cross. So the graph crosses the x-axis at x equals 0, and the graph touches the x-axis and turns around at x equals 18. Okay? All right, let's go back to our PowerPoint here, our notes. The next topic is the intermediate value theorem. Let me go back, go through that. Okay. So the intermediate value theorem, what it does is it won't tell you exactly what your 0 is, but it can help you figure out where one or where they may be located. So let f be a polynomial function with real coefficients. If f at a and f at b have opposite signs, so let's say if f at some value a is a positive number, but then f at the b is some negative number, if they have opposite signs, then what that means is the function crosses the x-axis somewhere between those values. So that means there's at least one value, c, let's call it c, for which the function is equal to 0. So in other words, there is going to be at least one x-intercept, one solution between those values, at least one solution between those values, where the equation, when you place it equal to 0, would have an actual x-intercept, would have a solution, would have a crossing of the graph. So we're going to take a look at proving the intermediate value theorem. We're going to take a look at number 7 on the homework. I'm going to go straight to the homework here. And I do have an example in the notes as well, but I'm going to look at the one in our homework. So look at number 7. It says, use the intermediate value theorem to show that the polynomial has a real 0 between the given integers. So your function is x cubed minus x minus 4. And we're trying to see if there is a 0 between 1 and 7. So what we'll do is we will evaluate the function at 1. Take note of what the sign is of that answer, and we will evaluate the function at 7, and also take note of the function value and sign at that particular value. So we've got f of x equals x cubed minus x minus 4, and we're going to evaluate it at 1. So we'd have 1 cubed minus 1 minus 4, replacing x with 1, okay? X cubed minus x minus 4, so 1 cubed minus 1 minus 4. So 1 minus 1 minus 4. So for number 7, we have 1 minus 1 is 0, so we have a negative 4. So notice that is a negative number. Just kind of taking note there. And then we're going to evaluate it at 7. So we'd have 7 cubed minus 7 minus 4. 7 cubed, pretty large number. That is 343. And then we have minus 7 minus 4. So 343 minus 7 minus 4, we get 332, which is a positive number. Okay? Which is a positive number. So we have a sign change somewhere between these two values, which indicates that somewhere between 1 and 7, the function crosses the x-axis. So we're going to select, let's read through what we have here. F at 1 is supposed to be less than 0. So we're going to select D here because we have to be careful and make sure we're choosing the one with the correct symbol. So f at 1 is less than 0, is negative. We said it was negative. So we want to make sure we select D. I'm looking at C also to make sure. But notice that C has the same sign, and that's not correct. F at 7 is not negative, it's positive. So it's going to be D. And it says f of x is a polynomial with f at 1 equaling negative 4, which is less than 0, and f at 7 equaling 332, which is greater than 0. So the function has a real 0 somewhere between 1 and 7 because of the sign change. So that means somewhere, let's take a look at it so you can kind of get a really good understanding of what this means. So I'm going to put the function into the y equals, so I can look at the graph, x to the third minus x minus 4. I'm going to hit graph. And I may even just go to the standard window now. So what this means is somewhere between 1 and 7. Look, here's 1, and then 2, 3, 4, 5, 6, 7. So here's 7 down here. Somewhere between 1 and 7, the function has a sign change. It crosses the x-axis. It's below the x-axis here, so it's negative down here at whatever these x values are, but then at some point it becomes positive up here. So it has a cross, it crosses the x-axis somewhere between 1 and 7, which indicates a solution. Remember that solutions are showing up as x-intercepts when you graph the function. Okay? All right, let's see what else we got here. So the last two questions here are asking us to kind of put together several different key pieces of information to then be able to look at the graph of the function. So let's go back to the notes quickly here. So we're looking at a graphing strategy. So graphing a polynomial function, it says use the leading coefficient test to determine the graph's end behavior. Find x-intercepts by setting f of x equal to 0 and solve the resulting polynomial equation. So you're going to solve it, finding the x-intercepts. And then keep in mind also that we can use our graph, our calculator's graph, to get more information about what the graph should look like. If your exponent on your factorizations, if they are even, then remember the graph touches and turns. If it's odd, in other words, the multiplicity, if the multiplicity is even, the graph touches and turns. If it's odd, it crosses. We can also find the y-intercept. That can help us when graphing. And then also, we might use symmetry, if applicable, to help us draw the graph. So you might be asked about symmetry. Usually, y-axis symmetry or origin symmetry are the two that we focus on when graphing. So y-axis symmetry is where you replace x with negative x, and if it results in the original function, if there's no change, if it's just giving you back the original function, then that means yes, we have y-axis symmetry. So that would mean the graph would basically mirror, the left and right sides would mirror each other. The origin symmetry, if you replace x with negative x and you get the opposite of the function, in other words, every sign is changed, then you have origin symmetry. You do not have to have either, okay? There are situations where you have neither. So let's take a look at an example. So let's look at number 8 here. So this one says, use the given function to complete parts A through E below. Part A says, use the leading coefficient test to determine the graph's end behavior. All right, so what you may want to do here is look at the graph on the calculator or recognize that you don't have a degree of just 2 here because this is a product, okay? This is a product. You have a 2 here, but then you also have a squared here. So your degree is actually to the 4th power here. Your degree is actually to the 4th power here, if you think about it. So for part A, we're going to say, and I'm trying to see, am I looking at? Yeah, this is part A, this is number 8. All right, so we're going to say for this one that the graph falls to the left and falls to the right. Here's why. The leading coefficient is going to be negative, and the degree is even. So what you might want to do is even look at it in the calculator or multiply this out if you're concerned that you might get it wrong. Multiply it out, okay? But this has a negative leading coefficient because this sign here would make that first term most definitely be negative. And then the degree is even, so it will fall to the left and fall to the right. They'll both be down the graph. And we can, like I said, look at the graph. Then it says find the x-intercepts. Well, this is where you're finding the solutions. Find solutions. Okay. So we have already factored for it. So we have -4 place equal to 0, x minus 1 squared. We're going to place that equal to 0, and x squared minus 9. We're going to place that equal to 0. Okay. So when we solve here, this becomes, if we just drop that square, this becomes x equals 1 with a multiplicity of 2. And then this one is x squared minus 9. So we're going to actually solve this by taking 9 over. And then we have x equals a plus or minus 3. So here we have x equals 3, multiplicity of 1, and x equals -3, multiplicity of 1. So here are our solutions. There are technically 3 zeros, but that one is repeated twice. So that's why the number of zeros matches up with a degree of 4. Okay, so the x-intercepts are -3, +3, and then 1. Okay, and it says at which zeros does the graph of the function cross the x-axis? Well, it crosses the x-axis at the zeros where there's an odd multiplicity. So the graph will cross the x-axis at -3 and +3. Okay? The second part says, at which zeros does the graph of the function touch the x-axis and turn around? Well, that's when you have an even multiplicity. So the graph touches and turns at 1. Okay? Then part C says find the y-intercept by computing f at 0. So I would take the function and I would replace x with 0. So -4, 0 minus 1 squared, and then 0 squared minus 9. Okay? So I've got -4, here -1 squared, here -9. Continuing, let's see what we get here. For part C, I'm sorry, for the y-intercept, I'm sorry. Continuing on, we've got -4 times 1 times a -9. So that is 36. So the y-intercept is 36. Okay. Determining symmetry here, that's next. So let's see what we have, if we have any symmetry. So what we're going to do is we're going to see by replacing x with -x, see what happens. So I'm going to take the function and I'm going to replace x with -x wherever I see x. So I've got -4. Inside here, I've got -x minus 1 squared, because it was positive x minus 1. So this is now -x minus 1. And then right here, it was x squared. Well, that's going to now be -x squared and then minus 9. So cleaning this up, we still have -4. We still have -x minus 1. Nothing changed right there. Well, I'm sorry. That negative, when we replace x with -x, is still negative. Right here, when we replace x with negative, that's squared. So that's going to go back to being a positive again. But unfortunately, this is not the opposite of the function, because in order for it to be the opposite, every sign would be an opposite sign. Every sign would have changed. And also, neither is it the original function, because that's still negative right there. So it's neither, we don't have odd or even symmetry. It's neither. Okay. And then part E is asking us to look at the graph. So there we can most definitely use our calculator. Why not, So I'm going to look at y equals. I'm going to plug it in. So I have -4 parentheses x minus 1 squared, and then parentheses x squared minus 9. Okay? So I just kind of scooted the paper down so we can make sure we plug in, that glare, plug in that function correctly. Okay? And I'm going to scoot it back up here because my graphing, the good thing is multiple choice, but I still can look at it on my calculator and just ensure that I'm choosing the correct graph. So I'm going to hit graph, and you may want to zoom out some. Look at your scale. They're going from a -185 to a +185 on the Y, and it's just a 10 by 10 on the X. So let's adjust our window to match up with theirs. That way we can get a good picture. -185 on the Y min and +185 on the Y max. Standard 10 by 10 on the X. Let's hit graph now, and I bet we'll get a better picture. Absolutely. So that would be D. And all I did again to ensure that I get the correct graph, or I choose the correct graph, I just used their scale and I put them in my window on my calculator. Okay. All right. Number 9 is just like that one just before. And yeah, so that really wraps up this section. Very short. Um, I will send this out, the link to the video, so that to be sure that you have access to this. And I might possibly go ahead and make a second video. I'll let you know. A second video for the 3.4, I'm sorry, for 2.2, section 2.2. So hope you all are having a wonderful day, and I will see you soon.